Hi guys, good to see you again. We're here for part two of our motion notes. And just like last time, we're going to start off by defining a few terms that are important to understanding motion for this set of notes. The first term is constant speed. Okay, constant speed is exactly what it sounds like. It's not changing, it's staying the same. So like the train in the picture there, once it gets going, rolling on a flat track, the speed will stay pretty much the same the whole time. So we would say it would be traveling at a constant speed. Now, instantaneous speed is just a little bit different. Instantaneous literally means at one instant, which means the speed something is traveling at any given time. There are really two ways that we usually determine instantaneous speed in the real world. For most of us, we do it by looking at our speedometer. And there's a picture of one up there. You see this one shows you speed in miles per hour and kilometers per hour, as a lot of them do. But anytime we glance at a speedometer, that's our instantaneous speed. As we speed up and slow down, that reading constantly changes. Another person who measures instantaneous speed is a police officer tracking your speed. When you use a radar or he uses a LiDAR device like one shown here, it's pinging you and getting your speed at one particular instant. Now, the third term is average speed. And average speed is a speed where we measure a total distance and divide it by a total time. It's not really the speed at any given instant, it's just what things average out to be. For example, if I ride from my house down to Georgetown, which is about 30 miles, and it were to take me an hour, then my average speed would be 30 miles an hour. But that doesn't mean that every time I look at my speedometer, it says 30 miles an hour. Of course not. There are times when you're traveling faster. There are times when you're traveling slower. But overall, 30 miles an hour is 30 miles an hour, which would be your average speed. Now, velocity is another term that we often see used interchangeably with speed, but it's just a little bit different. Okay? Velocity is speed and direction. Okay, so the example on the screen there, 45 kilometers per hour to the east, is an example of velocity. If it only said 45 kilometers per hour, it'd just be speed. But that indication of direction is velocity. Now, you'll remember from the last set of notes that we had, displacement is distance in a certain direction. So velocity then is displacement over time. Speed is distance over time. Just as the difference between displacement and distance has to do with direction, the difference between velocity and speed has to do with direction. Velocity is speed and direction. Then constant velocity. Well, we go, gee whiz, Stone, you already said what constant speed is. What the heck? Well, there's a twist. So you got to remember, velocity is speed and direction. So if velocity doesn't change, that means all that doesn't change. So your speed stays the same and your direction has to stay the same. And since direction is staying the same, this is straight line motion. A good example of how to indicate direction and velocity is not only can we do it with cardinal directions like north, south, east, and west, but we can do it with signs in mathematics, plus and minus. A positive velocity is generally associated with motion in a positive direction. Most of the time we think of that as going forward. Whereas it's possible to have a negative velocity. That just means motion in a negative direction. Those signs are another way of showing direction. So negative velocity, we usually call that going in reverse. Now, since velocity includes speed and direction, a change in velocity could be just a change in speed, just a change in direction, or both. So one way to change velocity is to speed up. Another way is to slow down. Or a third way is just to turn. In fact, if you don't speed up or slow down at all, but you turn, you're still changing your velocity. Now, another way to study motion and measure it and analyze it is to use a graph. And we've been graphing a lot this semester. I know you guys are good at it. So we want to talk about some particulars for motion graphs. And the first one we want to talk about is a distance versus time graph. It's also called a position versus time graph. And you've got to know that that's the same thing, distance versus time or position versus time. Because remember, distance is just how we measure your change in position. We went over that in the last set of notes. So if we look at this information here on the screen, we see that there's a little car, and the car is riding along, and when he gets to a certain mark that we're going to call our starting mark, we could start our timer. And as he got to 10 meters, we could measure the time it took to get 10 meters and write that down. And as he got to 20 meters, we could measure the time it took from the start all the way to 20 meters and write that down. And then at 30 meters, we could record the time from the start all the way to 30 meters. And finally, over my head back there would be 40 meters. We could measure the time for that too. And we could take these distances and these times and write them in a lovely data table like this. You see that there's our distances and there are our times. Now, if we've got a data table with two columns and they seem to be related data, we can plot them and see what we get. So here is a great example of a distance versus time graph. And you see that time is on the x-axis. We put time on the x-axis anytime we're measuring rates of change, because everything is per time, like per second, per hour, per something. And distance is on the y-axis. Now, when we calculate the slope of any graph, you learned in math class that slope is rise over run. And that really is a change in y over a change in x. Well, since distance is on the y-axis and time is on the x-axis, for a position time graph, this means that it's change in distance divided by change in time. And we already learned that the change in distance divided by the change in time, distance over time, is the formula for velocity. There. So that tells us that the slope of a graph is the velocity, or the slope of a distance time graph anyway. Not all graphs, of course, just the one we're talking about today, but its slope is velocity. This means we can tell a lot about the motion of an object that's been graphed by simply looking at the shape of the line. If we look at this very first graph on the left here, we see that the line's horizontal. Well, that means your distance isn't changing. What's the only way that your distance can't be changing? You got to be sitting still. So a horizontal line on a position time graph means you're stationary. It means you're sitting still. It means your velocity is zero. Now notice the graph in the middle. That's like the first one that we saw. It's angling upwards. It has a positive slope. Since slope is velocity, that means it has a positive velocity. But what would happen if you were coming backwards? Well, over time, you would be getting closer and closer to your original starting line. So your distance would be getting less and less. And that's what happens in this graph on the right. It angles downward. It has a negative slope. That means it's a negative velocity. Something is moving in the negative direction or moving back towards the start or the zero mark. Now, in the questions that go with these notes, one of the questions asks you to describe the motion for each one of these. You see that A is the blue line that angles downward. B is a green line that angles upward. D is a red line that angles upward, but the slope isn't as much as B. And C is a nice horizontal line. You've got to explain the motion for each of these four in a way that lets us know you can tell the difference between them and that you know what they mean. Okay? Well, good luck with your answers. And tomorrow, or excuse me, the next time we meet, we will have some more cool stuff for you to do. Have a great day.